Okay, now look at this example and try to define it. In this example here, you can see there is a screw and it has a mass of 200 kilo. And obviously, for this screw, the mass is not uniformly distributed. But here, we are given a radius of gyration about the circle center and also the mass center point G. So this means we can easily calculate the MMI of this screw about mass center point G. We already know the coefficient of kinetic friction between this screw and the ground. Okay, at this contact point, the kinetic friction coefficient is 0.1. Okay, now the target is to calculate the angular acceleration alpha of this screw and the tension force in this cable. So I think the first thing is to determine when this screw is moving. Its motion is the general plane motion. This should be easy to identify. Okay. Then we will need the free body diagram and the kinetic diagram. So let's have a look how to do. Okay, so this is a screw. And here you can see this screw is moving because we have a couple moment M, and this couple moment is counterclockwise. At the mass center point G, we must have a weight force W. At point A, we have a tension force from the code. At the contact point B between this screw and the ground, obviously we have NB reaction force. And we also have friction force at this contact point. My question here is, what should be the direction of this friction force at this contact point B? To left side or right side? And obviously we know it should be horizontal, okay? But to left side or right side? Now, you know, to determine the friction force direction, we have two steps. First step, we assume no slipping, we assume no friction. Okay. If no friction, what will happen? What will happen? Because of this code, this screw will still get a rotation. And in the meantime, it will be moving to the right side. So, whatever at this point B on this screw, its moving direction should be to right side, okay? And then, you know, the friction direction must be opposite. So here we will have friction FB. and this is kinetic friction, okay? Because there is slipping or there is relative motion between this sprue and the ground at point B. And that's the free body diagram. We have indicated all the external forces and moments acting on this sprue. Now, for the kinetic diagram, we established this conventional XY coordinate system, and here the positive rotation direction is defined counterclockwise. Okay, so in this one here, firstly, we can indicate alpha. We can assume alpha positive, okay, positive counterclockwise. But how about the acceleration at point G? This time, AG and alpha, they are not independent. Why? Why? Because in this problem here, we can easily define the IC point. So what should be the IC point? This is sprue. Okay, let me go back to this slide. Okay, my question here is, what should be the location? What should be the location of the IC point for this sprue when it's undergoing general plan motion? Should the IC point here at the contact point between this sprue and the ground? How do you think? What should be the location of the IC point when this sprue undergoes general plan motion? IC point here, correct? Contact point. You think of the contact point here? Any other answers? What should be the location of the IC point here? Okay, so this point cannot be the IC point. Why? When we define this point as the IC point in a rolling motion, in that case, it must be a rolling without a slipping motion. Yeah, because slipping occurs at this point. So definitely this point should not be the IC point. The IC point in this problem here should be point A. Okay, why? Because we normally can think no slipping between a chord AB and this inner hub of this sprue. Okay, no slipping at this point A. If no slipping at this point A, then when this sprue, including this inner hub, when they are undergoing general plan motion, when they are undergoing rolling, this point A is actually an IC point. Okay? Because this chord AB is instatic. So at any instant, point A must be 0. The velocity must be 0. Okay? Okay, if we can understand this, then let's go back to this diagram. And here, at point A, it should be the IC point. If this is an IC point, and if we assume alpha is counterclockwise, then that means at this point G, this AGX, its direction must be horizontal to right side. And this is related to the direction of alpha. For AGY, actually, because this screw is ongoing general plane motion, and it's on a flat contact surface. So this means at point G, if you look at the moving path of point G, it must be a straight line, horizontal. So at point G, AGY actually should be 0. But here, we still can indicate AGY in this way. Okay, so that's the diagram you need before you can solve this problem. Free body diagram and the kinetic diagram. Any questions? Okay, now a solution. Okay, here we have already defined this problem, and we have drawn the diagram, and we already know the mass of this screw, kg, and we know mu k, and we know the couple moment m. Okay, we don't know t, alpha, and ag, but here, as I said just now, here AGY should be 0. We don't know AGX. Okay. And in this kind of problem, and you know, alpha and AG or AGX, they are not independent. In this problem here, we can assume T and alpha, these two unknown positive in my following calculation, because point A is the IC point. So for this rolling without slipping problem at point A, we can have the relationship between AGX, and alpha. And this is the conclusion we worked out in week 3 when we study acceleration analysis in rolling without a slipping problem. And this means besides these 3 equations from equation of motion we can establish, we actually have one more equation. And we can use this equation to assist our calculation. Now, have a look. For the first equation, along x direction for translational component, we have T FB. Okay, FB is kinetic friction force because we already know kinetic friction coefficient. So we can express FB using kinetic friction coefficient 0.1 times the reaction force MB at point B, okay? And before friction force, we have a negative sign. On the right side, we have AGX, but we already know the AGX can be expressed using alpha, okay, using alpha. And AGX in this diagram, you can see it should be to right side if alpha is assumed positive counterclockwise. So for AGX, it should be positive. And that's the first equation. From the second equation, we can work out NB directly. And then for the rotational component, we can select point G for our calculation. And we will have our third equation. Look at equation 1 and equation 3. You can see we have alpha and T, these two unknown. MB is already known from equation 2. So we can solve this problem. And finally, alpha and T can be resolved. And that's the equation for this problem. Do you have any questions? For this kind of problem, it's a rolling without a sleeping problem, because we can find the relationship between AG, X, and alpha. So this kind of problem is basically as similar as the solution for rotation about a fixed axis problem we practiced in last week. Any questions? Okay, so if no questions, let's continue. Okay. Next, we will discuss even more difficult kind of problem. That's frictional rolling or similar problems. And firstly, we will talk about what this kind of problems present. And then we will use an example to see how to deal with this kind of problem. In this kind of problem, and it's a kind of a rolling problem. But in this kind of problem, if a sleeping occurs in the very beginning, you don't know. It could be a rolling without a sleeping problem, and it could be a rolling with sleeping problem. If it's rolling without a sleeping problem, then at the contact point between this rolling rigid body and the surface, this friction force must be static friction force, okay? But if it is roll with the sleeping problem, then this friction force will be kinetic friction force. Initially, you don't know. Anyway, we still can establish our three equations. Okay, the first two for translation component, and here we assume we already know external force P, the driving force P, but we don't know friction force F. Along x direction, we only have P and F. We know P, we assume we know P, but normally the friction force F is unknown, because at this moment you even don't know it's kinetic friction force or static friction force. We also don't know Ag, okay? Along y direction, we have N, reaction force N, but N may be easily resolved. For the rotational component, if our calculation is above the mass center point G, the expression here, we have one unknown alpha, okay? So, now, in these three equations here, we have three equations, but 1, 2, 3, 4, 4 unknowns. So we can solve it. So how to deal with it? We will need one more equation to assist us. Now, what we can do? Firstly, we assume no slipping. We assume it's a rolling without a slipping problem. If it's a rolling without a slipping problem, we will know this friction force must be static friction force. If it's static friction force, and if we know mu s, static friction coefficient, can we express the friction force here is equal to mu s times n? Can we? How do you think? Can we calculate the static friction force between this rolling rigid body and the contact surface using this equation? Using this equation. We watched a video in the week before last week when we studied how to determine the friction direction. Do you still remember that video? Okay, let me play that video again. Now look.
We are going to analyze how the coefficients of static and kinetic friction affect the amount of force needed to make it.
For static